Okay, so time for some algebra. So here's how you derive the Michaelis-Menten equation. We start with their reaction. The enzyme plus the substrate forms a rapid equilibrium with the enzyme-substrate complex, and that can break down into enzyme and product. So the rate of the forward reaction is called K1, the reverse reaction K-1, and this one is K2. So from this, we can write equations for the rate of formation and the rate of decay of the enzyme substrate complex. So the rate of formation of the enzyme substrate complex is just all the things coming towards the enzyme substrate complex. So there's only one arrow pointing towards ES. That's the arrow that we wrote K1 over. And in elementary steps, all you do is write the K for that arrow times the concentration of the stuff on the other side of the arrow. That's it. The rate of breakdown of ES so those are all the arrows going away from ES. That's going to be K-1 times the concentration of ES, because that's the only thing on the other side of that arrow, on the back end of that arrow. And also it could go the K2 direction, and also the thing on the back end of that arrow is ES. So there's our two elementary step reactions from this set of elementary steps. Also, we know that however much enzyme we put in, so the enzyme concentration total, I'm just going to use a T. That's too much to have to write each time. Is going to be equal to the concentration that is free enzyme plus the concentration that is enzyme substrate complex. That's just saying all the enzyme we put in only could have gone one of two places. It's either part of the enzyme, free enzyme pool or part of the enzyme substrate pool at any point in time. So what? Well, if enzyme total equals E plus ES, that means that E equals the total enzyme concentration minus ES, right? If I just move ES to the other side from that equation, yep. So the amount of enzyme equals E total minus ES, and I can sub that into that reaction. So the rate of formation of the enzyme substrate complex is K1 times the quantity, E total minus ES times the concentration of substrate. I just substituted in for total or free enzyme concentration there. All right, now we move on to the steady state assumption. The steady state assumption is that the rate of formation of enzyme substrate complex equals the rate of breakdown of enzyme substrate complex. In other words, DS over DT, DES over DT equals 0. The concentration of enzyme substrate complex is not appreciably changing with time. So that means I can simply take the rate of breakdown and set it equal to the rate of formation. So let's do that. Here's the rate of formation, K1 times E total minus ES times substrate equals the rate of breakdown, K-1 times ES plus K2 times ES. So why do I do this? Well, we don't have any way of measuring the concentration of enzyme substrate complex. But if I can somehow solve for an equation that tells me how much enzyme substrate complex there is in terms of things I do know, then I can actually turn this into something I can use in the lab. So I'm looking for an equation that says enzyme substrate complex concentration equals something. And once I get there, from there I'll be able to determine my rate of reaction in terms of things that I know. So now I've got this equation and I need to solve it for ES. And this is where the algebra can get a little bit ugly. Well, the first thing I'd better do is distribute that left-hand side, because sure enough, I've got an enzyme substrate complex in that complex expression. All right, so let's just distribute the K1 and the S. So that becomes K1 times E total times S minus K1 times ES times S. All I did was distribute K1 and S over the quantity E total minus enzyme substrate complex. The other side I'm not going to change. Well, I know that if I want to solve this thing, I'd better get all of the terms that have enzyme substrate complex in them onto the same side. So I'll take this term and add it to both sides. So now I've got K1 ET S equals K negative 1 ES plus K2 ES plus, now because I'm adding it to both sides, K1 ES S. All right, now what? Well, I've got three terms on the right that have ES in them. Let's undistribute ES. So this side's not going to change. I'm sorry, my brackets are going to get messier as I go. Now we're going to factor out ES times the quantity K negative 1 plus K2 plus K1 along with substrate concentration. That stays there. All right, if I want ES by itself, I need to divide both sides by this term. And honestly, I want ES on the left because that's how we're used to thinking of things, right? So I'm going to divide both sides by this term, and then I'm going to turn the equation around. So hopefully I can do that in one step without throwing anybody. So the numerator is going to be K1 ET S over the term I'm dividing by there, K negative 1 plus K2 plus K1S. So that's looking pretty good. Except I'd really love to get that K1 out of the numerator. And I don't want to kill any kittens. You know, Dr. Lubin and her inappropriate canceling thing always kills kittens. So if I want to get K1 onto the bottom, I need to divide each of the terms on the bottom by K1. So if I divide this whole right-hand side by K1 to get K1 on the bottom, it becomes this. I have to divide all of the individual terms by K1 so that no kittens die. This K1 cancels, but the other two don't. So I could instead express that denominator like this. That's just like saying 1/2 plus 3/2 is 4/2, right? And that's all that's left of that part of the term. So now I've gotten to equation 6 on my handout. And I did this. I got all of my K's grouped together because I happened to know that the definition for the Michaelis constant is K negative 1 plus K2 divided by K1. Gee, I wonder where that came from. So all of the rate constants, the K's, are constants. So I've lumped all of my constants into one spot, given them a better abbreviation, better because it's less hard to write. And so now I've simplified my equation for the enzyme substrate complex concentration to ET, something I know because I know how much enzyme I put in. Substrate concentration, which is going to be my X, right, when I graph this. Km, that collection of constants, plus substrate concentration. So I am almost to the Michaelis-Menten equation, except this is an equation for the concentration of ES. Well, why was I headed here? Well, because of the other important assumption, the rapid equilibrium assumption. So if we make the assumption that the equilibrium is reached rapidly, that means that formation of the enzyme substrate complex is rapid and then basically unchanging. So the enzyme substrate complex formation is not the rate determining step. The rate determining step has to be the catalytic step if the rapid equilibrium assumption is correct. If it establishes equilibrium rapidly, waiting for ES isn't the limiting step. So what is limiting is the catalytic step. So the initial velocity, how fast this thing is going, even right at the beginning, is going to be equal to the elementary step of that second reaction, which would just be K2 times the enzyme substrate complex. Because remember, that part of the reaction had enzyme substrate complex going irreversibly with a K2 rate to enzyme and product. So if this right here is our rate determining step, that means that K2 times the concentration of ES is the only thing that really matters for the rate of the reaction. It determines the rate. So that rate swamps the rapid equilibrium state. So if this is true, then that also means that enzyme substrate complex is equal to VI over K2, right? I just divided both sides by K2, and I can substitute that in for this. So here we go. VI over K2 equals ET times S over Km plus S. All right, except that I'd really like initial velocity by itself, so I'll multiply through by K2. And finally, I know that Vmax is determined by the substrate concentrate, or the enzyme, total enzyme concentration, and the catalytic step constant, K2 times ET. Well, that is just this. So I can write my final form of this equation. Initial velocity equals Vmax times substrate concentration over Km plus substrate concentration, QED. Thus, it is demonstrated, but in Latin. So there is the Michaelis-Menten